Unprofessional. All right. There we go. That's beautiful. All right. I was setting up the story about Baldwin's rules last time, so I'm just going to copy and paste what we had written last time. These are a set of empirical rules that describe basically what you can expect for cyclization reactions, intramolecular addition reactions. And it's based on orbital considerations and geometry, and in particular this idea of the Bürgi-Dunitz angle, where if you're attacking a pi star, you're going to do that from a particular approach, and that is about 105 degrees away from the pi bond that you're attacking, above the pi bond that you're attacking. So there's some factors to consider in these Baldwin's rules. First is ring size, and we'll talk about rings in the 3 to 7 range. After that, beyond that, geometric considerations aren't really a problem because you've got enough atoms to get where you need to be. But within this set, geometric constraints are important. The other factor is the hybridization of the atom that's being attacked. So as an example, I mean, this is hard to learn without examples. So let me give you one. This would be an intramolecular conjugate addition reaction. So we'll put an alkyne there, and then conjugated to it, we'll put a carbonyl. So this is a alpha-beta unsaturated carbonyl compound. And if you add a base to deprotonate the oxygen, you can do intramolecular 1,4 or conjugate addition with the oxygen attacking the beta carbon. 1, 2, 3, 4, 5. So you're going to make a 5-membered ring. And this would be the immediate product following that addition. 1, 2, 3, 4, 5. Okay? So yeah, the idea is you deprotonate the oxygen and those electrons attack there. So the hybridization of the atom being attacked, you still see? We're good? Yeah, okay. Hybridization of the atom being attacked is this beta carbon, which is sp, so that we would classify that as a dig cyclization. If it were something else, we would classify it as trig or tet. And then this issue of exo versus endo is something to consider. A cyclization is called endo when the atom that gets when the atom that is connected to the atom that gets attacked is part of the ring. In this case, the atom that's connected to the beta carbon that gets attacked. So this is the atom that gets attacked, but this is the atom that we worry about for endo versus exo. So the issue of hybridization is sp, sp2 versus sp3. The issue of endo versus exo is this atom that's attached to the one that gets attacked. And the question you ask is the atom that is in pink, is that part of the ring after the cyclization or not? If not part of ring, then we will call that an exocyclization. And so this would be, we would call this a 5-exo dig cyclization. And so Baldwin's rules, and I'm not going to copy them down because I don't think they're really worth memorizing, but you can look at them and you will hear people talk about them. If you're going to be doing a lot of intramolecular cyclization reactions, you should know them. Because if you're giving a progress report and you say, well, we tried this cyclization and it didn't work, then one member of your committee is going to ask, well, what kind of cyclization is that according to Baldwin's rules, and would you expect it to work, and why didn't you think about that? So you want to make sure you've thought about that when you're doing cyclization reactions. So Baldwin's rules say that a 5-exo dig cyclization works just fine. In contrast, you can use phone as webcam. If I wanted to do that, I would have asked you to. Okay, so we can change. Let's do a related situation, which will illustrate the exo versus endo feature again. So you can remove the proton from this oxygen, but it turns out the conjugate addition here, which would be 1, 2, 3, 4, 5. This is the beta carbon here that gets attacked, so we'll make that orange. This is the alpha carbon that is the one connected to the thing that gets attacked. If the attack were to occur, we would expect to see this enolate as a product, and except there would be an oxygen there. Just label the atoms again, 1, 2, 3, 4, 5. So this would be a 5, and then because the pink atom is part of the ring, we're going to call that endo. Yeah?
How do you know which one to choose as like your pink and your orange?
It's really when you attack the orange atom is the one that gets attacked, and the pink one is the one that the arrow goes to as that bond gets broken. Yeah. Of course, in this case, we've pushed the arrows all the way to that oxygen, but it would have been perfectly legitimate to just push the arrow to that alpha carbon.
Okay.
Yeah. So yeah, this is a 5 endo because the pink atom, the one that gets the charge after the orange atom gets attacked, that's within the ring. And this is called, because that orange atom is sp2 hybridized, this is 5 endo trig. And Baldwin's rules say not favored. Doesn't work very well, okay? In contrast, you could take the same basic structure, and this seems counterintuitive, and you can use the alkyne instead, and then that would be a 5 endo dig cyclization, which Baldwin's rules say are just fine. Okay? So you can get, oops, I lost some methyl groups there.
Ice is supposed to have a carbon.
Sorry?
The carbon.
Here? Carbonyl, is it supposed to still have one? I'm showing the final product, so the conjugate addition would be like this. Basically, if this were to attack, electrons would go there, and then you would get an intermediate with an enolate, which would get protonated on the alpha carbon, and that would give you this. Yep. So at first, to my eyes, it looks like it might be difficult for this oxygen to reach all the way over there. So let's just try to draw where the, we'll try to simplify things, erase some things, and let's try to draw where the LUMO is, and then maybe we can get some insight into why this reaction wouldn't be favored. So I'm going to erase everything. The LUMO of this alpha beta unsaturated carbonyl compound looks something like this. If we're looking at the alpha beta unsaturated carbonyl compound from above, we have this kind of situation. You know what? I'm still using pink and orange, and that we're using that for different purposes. Is that okay? Can we tolerate that? Sorry. So this is our view from above. Of course, in the plane of the page, there is a node, and below that node, there are corresponding lobes of opposite wave function sign. That was not good. Let's try that again. Okay. So, and remember the Berge-Dunitz, maybe I'll just draw this hydrogen here. The Berge-Dunitz angle tells you that you're going to want to approach this carbonyl carbon from above the plane, basically from this trajectory. So the angle we make between the pen and the page is about 109, 105. Okay? So ideally, a nucleophile should be able to approach from that angle. The problem is that this oxygen can't really get around there to do the attacking. And if we want, I suppose we could build a molecule in Spartan and see whether we can. It's certainly not going to have the MOs. I tried to do a calculation, but I didn't have enough time before class. So let's just draw that, at least that ketone starting. Oops, what happened there? No. Okay. Carbon, carbon, oxygen, oxygen, carbon, carbon. All right. So there's our structure. And it's drawing it in the S trans conformation. We would need to rotate around this bond to get this group here. I'm going to see if we have any information. Molecule not in database. Oh, but it is going to give us some conformational issues. All right, well there it at least gives us one. It's not showing us the oxygen where it should be, but this, you can't see where I'm pointing. So this atom that's going to get attacked, you have to think of the LUMO as being right here. And if the oxygen was here, could it's to the side and not directly straight on, okay? I mean, you want to see it from a different perspective? What questions do you have about that? In contrast, we can make that into a triple bond, clean that up a little bit, and then go here. And now it says that it's okay. And I'm not sure I understand why that's okay. Other than, yeah, so there's one with our nucleophile. Other than the possibility that with an alkyne, you've got pi orbitals in two different directions. So maybe I could draw this over in notability, if we try to draw this alkyne, you would have a pi star here coming out of the page. But you would have another pi star coming out perpendicular to the page. We'll use different colors. And so maybe, I don't know, but maybe the geometry works better for that kind of approach for the alkyne. What I've tried to do is justify these rules that are empirical based on orbital considerations. But you can see that when you try to do that, sometimes the explanation's unsatisfactory. I can see why this one doesn't work. That one makes sense to me. This one, not sure. So understand that these rules are empirical, which means they're based on people's observations, not necessarily theoretical. If we wanted to know more about this, we could do some calculations for transition state energies that lead to these products, and maybe we would see that the transition state energy is too high for this reaction to be favorable, but it's reasonable for that one. And there would probably be some insights in there. I just haven't done those calculations. So be aware of Baldwin's rules. Be aware of what people are talking about. Ring size, hybridization of atom being attacked, endo versus exo. And when you go to do a cyclization, just check and see whether what you're proposing agrees with Baldwin's rules or not. Okay? And it's really just a summary of observations that have been in the literature about cyclization reactions that work well versus those that don't. Probably based in orbital issues, but there you go. All right, anything more you want to say about that? I really don't think it's useful to try to memorize those. I've never bothered to memorize them. I mean, someday when our robot overlords deny us access to Wikipedia, it might be useful to know such things, but right now, you can just look it up. All right. So I want to say a little bit about elimination reactions. How many of you have heard of the E1CB reaction? Yeah? Okay. What's that mean? Don't remember? Okay.
I remember hearing it.
Right. So have you heard of E2 and E1?
Yeah.
Yeah? E2 is what?
Bimolecular elimination.
Right. Bimolecular elimination. And that means that there are two things involved in the rate determining step. If we were to write a rate law, this would equal some rate constant. We would have our alkyl halide, usually with a leaving group, whatever it is, could be anything, and then the base. And both of those are involved in the rate determining step, and if you want to accelerate the reaction, you can do it either by, well, in either case, the reaction's first order in alkyl halide and first order in base. E1 is sort of the SN1 version of the elimination reaction. It's unimolecular because the rate determining step is carbocation formation. And under, well, we can't. And under most conditions, that is all that matters. And so for the rate of this reaction, it is just the concentration of the alkyl halide that matters. And you can use very weak bases. All right, that's all familiar? Now, E1CB is also unimolecular. But it involves, although it can be more complicated than that, And it involves generally deprotonating first. Remember, the elimination reaction removes, you've got a proton on the beta carbon, you've got a leaving group on the alpha carbon, and we're going to eliminate to get an olefin. And so whether we deprotonate first or the leaving group leaves first, or whether it happens at the same time, is sort of what we've got here. In the E1CB, we're going to deprotonate first, and that is rate determining, and then leaving group leaves is fast. No, that's exactly backwards. Deprotonating first is fast, and then the leaving group leaves is slow. Sorry about that. It made sense to me when I was saying it, but it's not true. Deprotonating first is fast, then the leaving group leaves is slow. CB stands for conjugate base, because the thing that matters for formation of the product is the concentration of the conjugate base. So I will give you an example, and we'll talk about kinetics. Generally, E1CB reactions involve resonance stabilized anions. So here you have a ketone, a proton there, and a leaving group here. So we'll call, relative to the leaving group, we'll call this the beta carbon, even though we know it's alpha to the carbonyl. Okay, so what we're saying is basically you've got this rapid pre-equilibrium step where a base, in this case it's triethylamine, removes the proton. And the reason that can happen without the elimination occurring right away is that, is that the anion is resonance stabilized. Do you see how this is a resonance stabilized enolate? Okay. I'll just highlight that by reminding you that we can delocalize the charges there. So that conjugate base of our starting material is relatively stable. It survives for a while, and so this second elimination step is slow. At that stage, these electrons kick down and the leaving group leaves, and that gives you your alkene product, okay, with Cl minus as the leaving group. Right, and I guess I should also include the ammonium group. So this is our product. This is our starting material, which we'll call R with the leaving group. This is our base, which we will call B. This is our protonated base, which we will call BH+. All right, so kinetically, the rate of product formation is K2 times the concentration of, we've got to have somehow deprotonated, I don't know what to call it, RLG minus or something like that. So K2 times RLG minus, the anion. So it's unimolecular in this. Now, if we do a steady state approximation, and we won't derive this because you guys already know how to do that, I'll just get you started. We're going to say that the rate of change over the course of the reaction in the concentration of the conjugate base is 0. And so we're going to balance the things that come forward from starting material to give us this intermediate versus the two things, the reverse reaction and the forward reaction, that take away that intermediate. If we do that, you will come to a final rate law that looks like this. You've got K1 and K2 in the numerator. You've got the concentration of the starting material and the concentration of the base. And then in the denominator, you have K minus 1 times the concentration of the protonated base plus K2. All right, so that's what you'd get, from the steady state approximation. Now let's see under what situations, let's see what kinds of kinetics we might observe under different situations. So example 1 is, let's suppose that K1 is fast and K minus 1 is also fast, and that K minus 1 is greater than K2. All right? So then, what's the rate law going to look like? I could simplify it to what? If K minus 1 is greater than K2, then I could neglect the K2 term, right? K1, K2, R, L, G, B, K minus 1, B, H. And that looks complicated, but actually you've got K1 and K minus 1 there. Let's see, we got a plus. The acid dissociation constant for BH plus would equal H30 plus times concentration of B divided by the concentration of BH plus. So we could substitute, we could say that Ka divided by H30 plus equals B divided by BH plus. So we can substitute this out, and as long as we're keeping the pH constant, what this simplifies to is K1, K2, Ka, RLG divided by K minus 1 times H30 plus. All of this then becomes a constant, and you get an observed rate constant that's unimolecular in the concentration of your starting material. Okay, that's the classic E1CB mechanism. If your protonation and deprotonation are really fast relative to this step, then you're going to see basically unimolecular kinetics, even though, and it's going to look kinetically like a regular E1 reaction, even though you know, based on the fact that you've put in base, that that's not what happened. All right, and there's another case we could consider. Let's imagine case number 2 would be that K2 is fast, and so K1 is the rate determining step. If we take our rate law, what we're basically here, if K2 is fast, then that means K2 is much greater than K minus 1. So we can simplify that rate law. RLG B and then just K2 in the denominator, that cancels out and we get an expression that looks a little bit like an E2 reaction, right? So E1CB sort of describes this continuum, or sort of describes an alternative to elimination that involves removing the proton first, but you're seeing that based on these two scenarios that we're envisioning, we can have something that's unimolecular or bimolecular. There's sort of a continuum between the ideal E1CB reaction and then the classic E2 reaction. So people sometimes think about this in terms of those annoying overhead Moore-O'Farrell-Jenks plots. I think if I hold my, yep, ooh, that's a lovely square, isn't it? Okay, so let's just, right. Let's just imagine we have our starting material in this upper right-hand corner. You've got the beta proton, the alpha leaving group. And let's suppose that on the beta carbon we have either the presence or the absence of an electron withdrawing group. We also have a base as our starting material. And let's suppose this axis represents extent of deprotonation, whereas the y-axis represents extent of leaving group departure. iPads are annoying because if you want to write sideways, extent of deprotonation on the, extent of deprotonation on the x-axis, extent of leaving group departure on the y-axis. So let's just sort of follow through various mechanistic pathways. I'm going to use orange here because we used orange before for this same pathway. Leaving group departs, that's basically the same first step as an SN1 reaction, right? Okay, so in this corner we would have then a carbocation on the alpha carbon. Our proton would still be there on the beta carbon. We still maybe would or wouldn't have with electron withdrawing group, and we would have our base here. And then if the base removes the alpha proton, and then you get deprotonation, and that would get you to our alkene product. This used to be our alpha carbon, this used to be our beta carbon. Again, we have maybe the presence of an electron withdrawing group, and we have the conjugate acid of our base. Okay, so the orange is sort of the classic E1 pathway. Let's think about the classic E2 pathway. I'm going to choose purple for this because that was what we chose for the concerted reaction. Purple is just going to be the direct diagonal here where the leaving group leaves at the same time as we're doing deprotonation, right? So that's the E2 pathway. Now, with SN1 reactions, we never worried about, with SN1 versus SN2, we never worried about that corner, right? Because there was no way for the nucleophile to go in and make a bond first and then the leaving group leaves because carbon's too small. With deprotonation, that's a totally different story because it's totally possible for us to make this anion and then in the second step, the leaving group leaves. So I'll use a new color for that. We'll choose this blue color and we'll draw a line here across the top. That's make the anion and then leaving group leaves. And this is the E1CB. All right? And just like we saw for the SN1 versus SN2 comparison, this plot gives us a way to rationalize what will happen in a reaction if we remodel the energy landscape by changing the stabilities of any of these corners. So suppose we have a reaction that proceeds via E2 and it has a transition state here. We'll call this the E2 transition state. Let's examine some different effects that might happen. All right, so, and I'm going to use colorful arrows for this purpose, and we may run out of colors. So let's use this sort of green color for, let's say that we use a stronger base. Okay, so that's possibility one. What would that do to this energy landscape? Let's focus on the corners. Using a stronger base does what?
Increase the speed of deprotonation.
Okay, it should make it faster to do the deprotonation. I think maybe one way of saying that is that you raise the energy of this side of our landscape relative to that one. If the base is more reactive, that means its conjugate acid is correspondingly more stable. So we can view that either way, but let's just for consistency's sake say we're going to use, is that the same? No, that is not even the same color green. Oh well. So using a stronger base is going to take this corner and move it up in energy, and it's also going to take this corner and move it up in energy. All right? Now remember, along the diagonal, raising and lowering the corner has the Hammond effect. That is, if I raise the energy of the starting materials, one of the effects I'm going to see is that the transition state is going to move towards starting material. It's going to get earlier because the starting material is closer in energy to the transition state. But the other thing I have to think of is that when I raise this off-diagonal corner, it's the marble on a rolling marble on a sheet effect. That is, if I raise this, the marble's going to roll away from that corner. So we're going to see that effect as well, and we add them together doing vector math, and we get this overall change in the transition state. And notice that relative, if you think about where we were relative to where we started versus where we are now, we've got exactly the same extent of deprotonation in the transition state. But we have moved to way less leaving group leaving. And in this way, we've sort of moved ourselves towards a transition state that looks E1CB like, right? The base doesn't have to wait for the leaving group to leave in order to remove the proton, okay? Similarly, let's think about what if we use, well, let's use this color of red-green, or try to avoid red and green. Pink, yes. Let's use pink for use a better leaving group. And I didn't write over here, here is your leaving group. So if I use a better leaving group, what's that going to do? What should that do to which corners? Raise here and here? Okay, you're right, it will affect this opposite sides. Why do you say raise?
Well, because if you have a better leaving group, wouldn't it want to leave faster to form your carbocations?
Right, a better leaving group. Oh, hold on. Sorry. I am kind of wrong, aren't I? Here's where the leaving group's gone, okay? Sorry. If I had paid attention, up here, the leaving group is still there. It's down here, this edge, that the leaving group has gone. Sorry about that. So if we make it easier for the leaving group to leave, that's the same as taking this corner and moving it down in energy, stabilizing things, right? All right. So if we lower the energy of this diagonal corner, that's going to have, again, the Hammond effect. So if I lower the energy of the products, that means the transition state will again resemble starting materials more. So I'm going to just put another arrow there. That's the Hammond effect. If I lower the energy of this corner, that's the rolling marble on a sheet effect. We're going to see a pull perpendicular to the line towards this end. And if we do our vector math, the overall effect puts our new transition state here. And again, you can see that if we use a better leaving group, we get the same extent leaving group departure. Oh, I thought I had more room to write departure. Oh well. But way less deprotonation. That's kind of counterintuitive, isn't it? Because you think, oh, if I make the leaving group better, the leaving group ought to be able to leave earlier. But it's more like you get more bang for your buck, right? The leaving group can leave to the same extent, but less deprotonation is required. And again, we're moving this transition state much more towards an E1 reaction when we use a better leaving group. Okay, last one. What if we have a better electron withdrawing group on the beta carbon? What would that tend to do? Well, you would think that that would lower the energy of this anion, and I'm not really sure what it would do for any of the other corners. Am I thinking through that wrong, or is that?
The other corner would go opposite to it because it's next to a carbocation.
Okay, right. Nice. Okay, so maybe having an electron withdrawing group here adjacent to a carbocation could increase this energy, decrease that energy. Effectively, that's the same overall effect, and so that's going to take our transition state and move it here. So using the better electron withdrawing group actually does, because there's no effect on starting materials or products. So that's going to give us purely the rolling marble on a sheet effect, and that's going to get us a transition state that has less leaving group departure and more deprotonation. Okay? So, a few things you can do. If you want to bias your reaction towards an E1CB mechanism, use a good electron withdrawing group. That makes great intuitive sense, and that's also what the energy landscape analysis gives you. If you want the reaction to be more E1CB-like, then using a stronger base can get you to having to have less leaving group departure before the deprotonation happens. In contrast, if you use a better leaving group, that's going to tend to push you more towards an E1 type mechanism or keep you at an E2 regime. All right, so just some sort of ways to think. I don't know why you would want to change a reaction mechanism in a practical sense if you were doing a synthesis, but physical organic chemistry is all about understanding the physical chemistry of the reactions that we're doing, and so understanding mechanism and what factors influence them can be really important. All right, I think that basically takes us through chapter 10, which is good because we are done. All right, I will see you next time. I've posted the key to the practice exam problem set 3. I'll do the same real soon with problem set 4. And all of those, you'll be able to report that you did them at the end of the semester.